Okay, so now let us look at the betweenness centrality. The betweenness centrality of the vertex is computed as the sum of its fractions of the shortest paths. So let us say we want to compute the betweenness centrality of vertex I. So what we're going to do is we are going to consider all the pairs of vertices j and k, which are not I, and see what is the total number of shortest paths between j and k, and what fractions of these shortest paths between j and k go through I. So that's what this fraction indicates. So SPJK of I indicates the number of shortest paths between j and k that go through I, and SPJK simply indicates the total number of shortest paths between j and k. So we're going to find this fraction of the shortest paths between j and k that go through I, and sum over all such fractions for all possible node pairs jk other than I. So we can use the breadth first search algorithm to determine this. So all we need to do is run the breadth first search algorithm once for each vertex, similar to closeness centrality. So the time complexity is going to be v plus v square. So before we do this, let us kind of have an intuitive notion or feel of how we really can interpret betweenness centrality. So let us take this graph. Now we can actually determine all these fractions using betweenness centrality. So using the breadth first search algorithm, which we'll do soon after this. But let us try to interpret the fractions of the shortest paths. Now let us pick up, say, node 1. Now, of course, there are all possible combinations of node pairs. Now, quickly we'll realize why I just listed these node pair. Okay, so but let us consider this node pair 0, 5. So between 0 and 5, there's only one shortest path, which is 0, 1, 5, and that shortest path goes through node 1. So there's only one shortest path between 0 and 5, and that one shortest path goes through node 1. Now let us pick up node pair nodes 0, 6. Now how many shortest paths are between 0 and 6? One shortest path is like 0, 2, 4, 6. So shortest path length is 3. There's another shortest path 0, 1, 5, 6 of length also 3. Those are the only two shortest paths between 0 and 6. So there are a total of two shortest paths between 0 and 6. And one of those two shortest paths, which is 0, 1, 5, 6, goes through 1. So 1 over 2. So that's a fraction of the shortest paths between two vertices 0 and 6 that go through a particular vertex 1. So let us pick again pair 0, 7. The shortest path is 0, 1, 5, 7, which is of length 3. And that's not the only one shortest path. There's one more between 0 and 7. 0, 2, 4, 7. So that's another shortest path between 0 and 7 of length 3. So out of those two shortest paths, one of them go through node 1. What about the pair 2, 5? So there are three shortest paths: 2, 4, 5, 2, 3, 5, and 2, 1, 5. So we have three shortest paths between 2 and 5, and one of them goes through node 1. So it's 1 over 3. So that's the betweenness fraction. Now, why I did not consider all other possible node pairs? You could consider, but let us pick up something like 3, 6. So 3, 6. We have 3, 4, 6. That's the shortest path of length 2. There is one path, and 3, 5, 6. It's also a shortest path of length 2. So there are two shortest paths between 3 and 6, and none of them go through node 1. So the fraction for node 1 with respect to the path 3, 6 is going to be 0 over 2. There are two shortest paths between 3 and 6. So 2 is in the denominator, and the numerator is 0 because none of those two shortest paths go through node 1. So it's 0 over 2, which is 0. So we are listing here only all the non-zero fractions for the number of shortest paths between two vertices that go through node 1. So now we will sum all these fractions, and that will get us the betweenness centrality of node 1. Now you should realize why for node 0 we list its betweenness centrality as 0, because No other pair of vertices, no pair of vertices go through node 0 for shortest path communication. If you look at this graph, 1, 2 can reach each other right away, and 1, 3, yes, go through 1, 2, 3, and so on. None of the vertices in this graph have to go through node 0 for shortest path communication. So that's why the betweenness centrality for node 0 is 0. Similarly, for 6 and 7, none of the vertices in this graph, or none of the pairs of vertices in this graph have to go through 6 or 7 for shortest path communication. So the betweenness centrality is 0. So for node 3, it's on shortest path between 2 and 5. There are 3 such shortest paths between 2 and 5. We just saw 2, 4, 5, 2, 3, 5, and 2, 1, 5. And one of those 3 shortest paths go through 3. Now, no other node pair would need to go through vertex 3 for shortest path communication. So we have to just say betweenness of node 3 is just this value of this pair 1. Similarly, node 2, these are the fractions of the shortest paths that go through node 2 between all these node pairs. So the sum is 4. So if you do this for every vertex, what we get is the betweenness centrality of each of these vertices. Okay, so the critical thing in getting the betweenness centrality of a vertex is to find this fraction of the shortest path between any two nodes that go through that particular vertex. So you have to consider all possible node pairs and do this computation. So it looks like it's a more time-consuming process. So actually, betweenness centrality is the most time-consuming centrality metric of all the metrics that are out there that we're going to see. Alright, so there is another graph which we did already for eigenvector and degree centrality, and if you look at the fractions, so these are the fractions of the shortest paths that go through vertex 5. So sum of all these fractions is 10, so that's betweenness centrality of vertex 5. Now in this graph, for vertices 1, 6 and 7, none of the other vertices go through those vertices for shortest path communication. So the betweenness centrality is 0. So if you look at it, for example, vertex 1, 0, 2, 0, 3 or 0, 4, all these pairs will not go through vertex 1. So the betweenness centrality of vertex 1 is 0. Similarly, for 6 and 7, none of the pairs of vertices will need to go through 6 or 7. So in this case, the betweenness centrality for 4 as well as for 3 comes out to be 12. Okay, so that's the largest betweenness centrality. Now if you go back to the example on eigenvector centrality on this graph here, we found 0 and 2 to have the largest eigenvector centrality, and we found 0, 2, 3, 5 to have the largest degree, whereas now for betweenness 3 and 4 has the largest betweenness. So that is something we have realized, that the ranking of the vertices based on the centrality metrics could be different, and that's what we are going to also look at in the future modules. So now, how to determine the betweenness centrality of a vertex? So as I said, we need to determine all these fractions. So what we're going to look at is how to determine one such fraction. So given this graph, what we want to find is what is the fraction, which I call it as betweenness centrality for a vertex C with respect to the pair AG. So we're going to find what is the total number of shortest paths between A and G, and what fractions of these shortest paths go through C. Okay, so that's what we're going to find out. So in order to do this, so from exam point of view, this is what I'll ask you. Given a graph, and I'll ask you to find the betweenness centrality of some vertex with respect to a pair of vertices. So if you're given such a question, your first step is to run the breadth-first search algorithm from the two end vertices A and G. So in this case, we'll run breadth-first search starting from A. So what I've shown here is the level numbers of the vertices on the breadth-first search tree starting from A. So A is said to be at level 0. Its two neighbors B and D are now said to be level 1. So these are the tree edges. Now from B we can go to F and C. Sorry, from B we can go to F. So the level number of f is going to be 1 more than the level number of b, which is 2. Now from d, you could go to f, but f has been already visited through b, so this edge will become a cross edge. Now from f, we can go to c and e, so those two vertices are said to be at level 3. Now from c, we can go to g, which is at level 4. Now from E, we don't need to go through G because G has been already visited, so this becomes a cross edge. So this is how you find the level numbers of the vertices and put them together, put all the three edges together to visualize a breadth-first search tree. Similarly, you can run breadth-first search starting from G and find the level numbers of the other vertices. So it's going to be 0 for G, C and E are at level 1. Now through C we can reach F, which will be at level 2. Through F we can reach B and D at level 3, and through B we can reach A at level 4. So this is the first step to find the level numbers of the vertices starting from the two end vertices. So now what we want to find is the number of shortest paths from the root to the other vertices. Now for this, let me give you a general principle idea. So if you have the root and you have gone through and you have built the breadth-first search tree, so let us say there is a vertex V for which we want to find the number of shortest paths from the root to that vertex V, and let us say vertex V is at level L. Now in the breadth-first search tree, which involves only the three edges, you could also find out that there are three vertices which are the predecessors for vertex V and at level L minus 1, so the immediately previous level. So we are going to find the number of shortest paths from the root to each of the vertices on the order of the level numbers. So when we have to find the number of shortest paths from the root to vertex V at level L, we would have definitely found the number of shortest paths from the root to each of the predecessors of V at the L level, which is L minus 1. So let us say these are the three predecessors, U1, U2, U3. And these are the number of shortest paths from the root to each of these predecessors. So all you have to do is now add up all these shortest paths. So there are three shortest paths from the root to U1. So we'll simply take this edge to reach V. So still you'll have three shortest paths from root to V. Similarly, there's one shortest path from root to U2. We'll just continue that edge. So it's going to be one shortest path from root to V going through U2. For U3, there are four shortest paths from the root to U3. So we can take any of these four shortest paths to U3 and then go through this edge to reach V. Okay, so sometimes you may not have more than one predecessor. So if you have something like this where the root is there and you have four shortest paths to vertex U at level L minus 1, and what you want to find is the number of shortest paths from the root to V. So we can take each of these four shortest paths to reach U3 and then take this edge to reach V. So there will be only four shortest paths from root to vertex V. Okay. So why we did this? So once we find the level numbers, what we have to find is the number of shortest paths from the root to the other vertices. So from the root to itself, which is A, in this case, on the shortest path 3 rooted at A, the number of shortest paths from the root to itself is 1. And once we get that, we can use the rule that we just described to find the number of shortest paths from the root to any other vertex. So we have to go through the level based on the level numbers. So for B and D, which are at level 1, the number of shortest paths will be whatever is up to A. That's only predecessor, right, for B and D, which is A. So that same number of shortest paths will continue to the downstream vertices B and D. So there's one shortest path from A to itself, and we have to take this edge to reach B. So there's only one shortest path from the root to B as well as from the root to D. So now let us look at the next level. We have F. So what we want to again find is the number of shortest paths from the root to F. Now you can see F has two predecessors at the earlier level. There's one predecessor B, which has one shortest path from the root to B, and there's one predecessor D, which has one shortest path from the root to A. So the number of shortest paths from the root to F is going to be sum of the number of shortest paths from the root to the predecessors. So it's going to be 1 plus 1, which is 2. So now we're looking at the next level vertex, which is C as well as E. So the number of shortest paths from, of course, C and E has only one predecessor, which is F. So the number of shortest paths from the root to C is going to be the same as the number of shortest paths from the root to F. So that's going to be 2 shortest paths. Now from the root to G, what we have to do is find again the number of shortest paths from the roots to the vertices at the earlier level. So the earlier level is going to be C and E. We have 2 shortest paths from the roots to C and E. So you have to just add up the 2 shortest paths, so that will be 4. So that's the number of shortest paths from the roots to the other vertices. Now similarly we can do on this first actually starting from G, which is said to be at distance 1 to itself. Number of shortest paths from the root to itself is 1. Now for C and E, they are directly connected to G. So the number of shortest paths from the root G to C is going to be also 1. And E is also directly connected to G. So it's going to be 1 shortest path from G to E. Now there is one shortest path, one vertex at level 2, and there are 2 vertices at level 1, C and E. So what you have to do is find the number of shortest paths from the roots to the predecessors. So the predecessors, so this is at level 2 for F. The predecessors are going to be at C and E. So all you have to do is add up the number of shortest paths from the roots to each of those predecessors. So we have one shortest path from the root to C, another one shortest path from the root to E. So 1 plus 1, 2 is the number of shortest paths from the root to F. So now you have B and D. So far we have degree 2. So B is degree 2. Number of shortest paths from. Let me take it back. So we want to find for say B. So there's only one predecessor at the earlier level. So whatever is the number of shortest paths from the root G to F is same as the number of shortest paths from the root G to B. Similarly for D, there's only one predecessor at the earlier level, which is F. So the number of shortest paths from G to D is the number of shortest paths from G to F. So finally we have A. So we have an edge now. So for A there are 2 predecessors at the area level. So for B and D we found we need 2 shortest paths from the root G. So it's going to be sum of these 2 shortest paths, which is 4 shortest paths from root G to A. So now what we want to find is the betweenness fraction of C with respect to the pair AG. Now in order to continue doing that and get a non-zero value, we have to make sure one condition is satisfied. So this vertex C, so the level number of vertex C on the shortest path tree, say starting from A, should be less than the level number of G in the shortest path tree of A. And similarly, the level number of C should be less than the level number of A in the shortest path tree of G. So we have 2 end vertices. So we have to have the number of shortest paths and the level numbers of the vertices. So level number of C in the shortest path tree of A, which is this, is 3, and it's less than the level number of G. So basically what we want to find is whether C is on the shortest path from A to G. Similarly from G to A, the level number of C is going to be 4, which is this. So this is the number of shortest paths. This is the level number. So the level number of C from G is going to be 1 and A is going to be 4. So 1 less than 4, so it's fine. So both conditions are satisfied for the level numbers. So now you can go ahead and say what is the number of shortest paths from A to G that go through C. So that's the product of the number of shortest paths from A to C and the number of shortest paths from G to C. So whatever is from A to C, that many shortest paths, and whatever is the number of shortest paths from G to C, that many shortest paths that go through C. So the number of shortest paths from A to C is going to be um, 2, from this shortest path 3, we can find the number of shortest paths from A to C. The number of shortest paths from G to C is 1. So we take the product of these two numbers, which we get 2, which is the number of shortest paths from A to G that go through C. Okay, so that's the numerator, number of shortest paths from A to G that go through C. And the total number of shortest paths from A to G is the denominator, and that's going to be 4. So the number of shortest paths from A to G is going to be 4. So the betweenness fraction is 2 over 4. Okay. So let us do one more example. So what we want to find is the betweenness fraction of a vertex 4 with respect to the node pair 1, 7. So we will run the breadth first search starting from 1, and again another breadth first search starting from 7. So what will determine is the level numbers. So 1 is at level 0, its two neighbors are at level 1, then 3 is at level 2, 4 is at level 3, 5 is at level 4, and these two neighbors 6 and 7 at level 5. Similarly, if you start breadth first search from vertex 7, which is at level 0, 5 and 6 will be at level 1, 4 will be at level 2, 3 will be at level 3, and so on. So what we want to find is the betweenness fraction of vertex 4 with respect to the node pair 1, 7. So 4, let's look at the breadth first search tree starting from vertex 1. So the number of shortest paths, or this actually indicates the level number. So the level number of 4 is 3, and which is of course greater than the level number of vertex 1, the root, which is 0. And 1 through 7. Alright, okay. So in the breadth first search tree starting from vertex 1, the level number of the vertex 4 is less than the level number of vertex 7, which is 5. Similarly, in the shortest path tree rooted at 7, what we're going to find is what is the distance from the root to vertex 1. So that's going to be level 5. Now what is the other so number of nodes that go through between 1 and 7. Okay, so the level number of 4 is less than the level number of 1 in the shortest path 3 rooted at vertex 7. So the level number condition is indeed satisfied. Okay, so now we can get all these fractions, sum them up, and that will be betweenness centrality of vertex 4. So once we get the level numbers, we can also compute the number of shortest paths from vertex, the root, to the other vertices. So the root here is vertex 1, so the number of shortest paths from the root to itself is 1, and you have 0 and 2, so it's going to be the same as only one predecessor, so it's also one shortest path. In the case of 3 at level 2, we have to just add the number of shortest paths from the root to 0 and from the root to 2, so it's going to be 2. So whatever is for 3, that's what 4 is going to get in its two shortest paths. Similarly, 5 is going to get whatever 3 and 4 has. So now for 6, you'll have there's only one predecessor at the earlier level. So 6 is at level 5, there's only one predecessor at level 4. So whatever is the number of shortest paths from the root to 5 is going to be the same as the number of shortest paths, say, from the root to 6 or 7. So we go through the same process, and what we need to now do is take the product of the number of shortest paths from 2 or 1 that go through node 4. And looking at the figure here, 1 through 7 that go through node 4. So there are two such shortest paths. Now how to determine this based on what we have? So it's a product of 2 and 1, as I say. So 2 is the number of shortest paths, say from 1 to 7 that go through node 4. Similarly, you can find the number of shortest paths from the root 7 to the rest of the vertices, and you will find out that there's only one shortest path from 7 to 1 that goes through node 4. So it's going to be 2 shortest paths. 2 times 1 is 2, and the betweenness centrality of node 4 with respect to the pair 1, 7 is going to be this 2 divided by 2. So 2 is the total number of shortest paths between 1 and 7, 1 going through 0 and 1 going through 2. And among those 2 shortest paths, 2 of those shortest paths between 1 and 7 go through node 4. So the betweenness fraction is going to be 2 over 2. So this is the general principle I explained. So if you have a vertex V at level L, you should have by then found what vertices are at level L minus 1. So you keep track of the number of shortest paths from the root to each of those predecessors at the earlier level, and just sum up the numbers that will get you the number of predecessors at level L. Now you don't need to really have more than one predecessor, so something like this is okay too. So you have 4 shortest paths from the root to a vertex U3, and then probably an H2 vertex V from U3. So vertex U3 is said to be at level L minus 1 and vertex V at level L. Okay. So regarding the level number prerequisite, so the prerequisite is this. So if you are looking at finding what fractional shortest paths between A and B go through C, so from the results of breadth first search on to find the number of shortest paths, you should have figured out how to do that. Okay, so looking at the vertex C with respect to the pair AB, so the level number of C should be less than the level number of B in the shortest path 3 rooted at A. Similarly, the level number of C should be less than the level number of A in the shortest path 3 rooted at B. So this condition, these two combinations of conditions should be satisfied for the betweenness fraction of a vertex with respect to node pair AB to be greater than 0, otherwise it will be 0. Okay, so let's do a couple of examples. So given this graph, let us pick the pair 3, 6. So now we have to run breadth first search from 3 and breadth first search from 6 with those two vertices as the root for the respective breadth first search 3. So 3 is at level 0, then 1, 2, 4 and 5 are said to be at level 1 and 6 is at level 2. So 6 is at level 0, 4 and 5 are at level 1, then 2 and 3 will be at level 2 and 1 will be at level 3. Okay. Alright, so in order to find the betweenness for vertex 1 with respect to the path 3, 6, what we have to make sure is the level number of vertex 1 is less than the level number of vertex 3 in the shortest path 3 rooted at 6. So shortest path 3 rooted at 6, the level number of vertex 1 is 3. Is it less than the vertex number of vertex 3 in the shortest path 3 from 6, which is 2? So is 3 less than 2? No. So that is why we can say the betweenness of vertex 1 with respect to the path 3, 6 is going to be 0. So let us now do the betweenness of 4 with respect to the same path 3, 6. So the level number of 4 is 1, is less than the level number of 3, which is 2. So that means we are going to also we have to check for 4 with respect to the 3 breadth first search tree starting from 3. So the level number of 4 in the breadth first search tree is 1, and the level number of 6 is going to be 2. So 1 is less than 2 on this breadth first search tree. So since this condition is satisfied for both the graph, for both the best first search trees, we can confidently say the betweenness fraction for node 4 with respect to the path 3, 6 is greater than 0. Okay, so that we can stop.